Hello everyone and welcome. In the next few minutes, we are going on a deep dive into one of the most critical pillars of statistics and data science, that is hypothesis testing. Whether you are a beginner trying to grasp the concepts or a practitioner looking for a refresher, this guide is for you. Let's start at the very beginning. What is hypothesis testing? Imagine you are a detective. You have a theory about a case. Maybe you think a certain person is the culprit. You can't just arrest them on a hunch. You need to collect evidence and then you need to weigh that evidence to see if it is strong enough to support your theory. Hypothesis testing is exactly that, but for data. Formally, it is a statistical method used to make inferences or draw conclusions about a population based on a sample. We can't always measure everyone, so we take a sample and use it to test a claim. For example, a pharmaceutical company might claim a new drug is effective. We can't give it to every patient on earth, so we test it on a sample and use hypothesis testing to see if the results are convincing. Every hypothesis test has two opposing statements. First, we have the null hypothesis. This is the statement of no effect or no difference. In our drug example, the null hypothesis would be that new drug has no effect on blood pressure. It's the assumption that nothing interesting is happening. The second is the alternative hypothesis. This is the challenger. It's a statement that contradicts the null hypothesis, representing the effect you want to prove. In our case, the new drug does lower blood pressure. This is what the researcher is hoping to find evidence for. The whole point of the test is to see if the evidence from our example is strong enough to reject the status in favor of the alternative. The second is the alternative hypothesis. This is the challenger. It's a statement that contradicts the null hypothesis, representing the effect you want to prove. In our case, the new drug does lower blood pressure. This is what the researcher is hoping to find evidence for. The whole point of the test is to see if the evidence from our example is strong enough to reject the status in favor of the alternative. Now, as a detective, you can make mistakes. You might think someone is guilty when they are innocent, or you might let a guilty person work free. In hypothesis testing, these mistakes have names. That is type 1 error, type 2 error. Type 1 error is false positive. This is the guilty until proven innocent error. It is when you reject the null hypothesis when it is actually true. You conclude the drugs, but it does not. The probability of making this error is our significance level alpha, and we set this in advance, usually at 5%. Next one is type 2 error, that is false negative. This is the letting the criminal go free error. It's when you fail to reject the null hypothesis when it is actually false. The drug works, but your test failed to detect it. The probability of this error is called beta. Finally, we need to decide on the direction of our test. In our alternative hypothesis, directional or not. A one-tail test is used when we expect an effect in a specific direction. For example, the new teaching method improves test scores. We are only looking for an increase. Second one is a two-tailed test. It is used when we just want to see if there is a difference in any direction. For example, this new drug alters blood pressure. It could make it go up or down. We just want to know if it is different from the current treatment. Two-tailed tests are more common and more conservative. So, how does this actually work in practice? We follow a standard recipe with 6 key steps. Let's break them down. State the hypothesis. This is where we write down our formal statements. Let's say we are testing if the average height of the men in a city is 175 centimeters. Here null hypothesis is u equal to 175 centimeters. That means the average height is 175 centimeters. Here alternative hypothesis is mu not equal to 175 centimeters. Means the average height is not 175 centimeters. We are using a two-tailed test here. Step 2 is set the significance level alpha. This is our threshold for making a type 1 error. We decide how much risk we are willing to take. The standard is 5% or alpha equal to 0.05. In more critical fields like manufacturing or clinical trials, we might use 1% or 0.01. Next, step 3. Select the appropriate test. Choosing the right tool for the job is crucial. The choice depends on your data and what you are comparing. Are we comparing a sample mean to a known value? A t-test. Are we looking at the relationship between two categorical variables? A chi-square test. We will cover all of these in detail later. Next, step 4. Compute the test statistics. This is a mathematical part. We calculate a number from our sample data. Think of it as a standardized score that measures how far our observed data is from what the null hypothesis predicts. The formula varies by test, but the general idea is observed value minus expected value by standard error. Next, step 5. Find the p-value or critical value. This is where we determine the strength of our evidence. The p-value is the star of the show. It's the probability of getting a result at least as extreme as the one we observed, assuming the null hypothesis is true. If our sample mean is way off from 175 centimeters, the p-value will be tiny. The critical value approach is an older method. We define a rejection region in our distribution. If our test statistics falls into that region, we reject null hypothesis. Next, step 6. Make a decision. Finally, the verdict. If the p-value is less than the alpha value, p less than alpha, we reject the null hypothesis. We have enough evidence to support the alternative. Another option is if the p-value is greater than or equal to alpha, means p greater than or equal to alpha, we fall to reject the null hypothesis. We don't have enough evidence. Remember, we don't accept the null. We just say we couldn't find enough evidence to shoot it down. Now that we understand the process, let's talk about the tools. This is where we get hands-on with the most common statistical tests. We will start with the workhorse of data science, the t-test. There are 3 main flavors. First one is one sample t-test. The one sample t-test is used when you want to compare the mean of a single group to a known or hypothesized value. For example, a company claims their light bulbs last 1000 hours. You buy 30 bulbs, test them and get an average of 980 hours. The one sample t-test will tell you if that 20-hour difference is just random chance or a statistically significant deviation from the claim. The assumptions here are that your data is roughly normally distributed and your sample is random. Next test is two sample t-test. Next we have the two sample t-test. This is used when you want to compare the means of two independent groups. Think of it as an A by B test. For example, you are comparing the average exam scores of students from two different classrooms. The groups are separate and unrelated. A key point here is deciding whether to assume the groups have equal or unequal variances. If they are unequal, we use a version called Wells t-test, which is often the safer default choice. T-test. Finally, there is a paired t-test. This is for situations where your two sets of data are not independent but are linked or paired. The classic example is a before and after study. For instance, you measure the blood pressure of 20 patients, give them a treatment and then measure their blood pressure again. You are not comparing two different groups. You are comparing the change within the same group. This test is more powerful because it controls for individual variation between subjects.